welcome. We are going to do basically several stages of this talk, and at each of the situations where we show pictures, where we have a context switch or so, just feel free to shout some questions, because we want to have it a bit more interactive. So this is about pypy, new Python implementation that we have been working on for 3 years now. One of the talkers, actually, Rigo, is not here. He's one of the initiators, also together with Christian, who's sitting here. He couldn't come. He was basically very exhausted. We had a lot of work in the last month, actually, to get a lot of things, also releases and EU reports and all kinds of stuff finalized. And so he's basically now in Switzerland in the mountains skiing and relaxing a bit. Okay, so let's first talk a bit about how many of you actually know Python or have been programming in Python a bit. Okay, and how many know what a virtual machine is, how it works? Okay, that's about half, so that's good to know. So Python is actually a virtual machine architecture. It has a parser and a compiler, which takes a source code program, transforms it into bytecode, and then you have a virtual machine looking at the bytecode and interpreting, just like the JVM, the Java virtual machine does it, interpreting these bytecodes and executing all kinds of operations, and actually to make your program work the way you want it to be. It's a strong, dynamically typed language. I think the Dylan people yesterday and some other people mentioned this already. There's always some kind of confusion. It is so that unlike something like BASIC or Visual Basic or whatever, it does have strong types. So you have an integer, you have a string. It's not automatically converted into an integer or something. It's really an integer, and you get type errors if you try to do something that you cannot do with strings if you want to treat it as a number. So it's dynamically typed in the sense that you don't have to statically declare all the time what the type of each variable is. And it has a rather clean object model at various levels, especially also the C level. It's about a 10-year-old language, but even if you look today at the C code, how the virtual machine is implemented in C Python, it's really rather readable C code. And that's kind of like a very good thing that you can at all levels basically understand and relate the various concepts to each other. Okay, so next one. So what Python implementations do we have today? Today, there are a lot more experiments and things going on, but these are like currently the main implementations. We have CPython, which is the thing that everybody refers to as Python. And we have Jython, which is compiling a Python source code to Java bytecode. So it directly executes on the Java virtual machine. It integrates quite totally with Java. So you can subclass Java classes. It's actually, I think, in one recent survey, Jython was the #1 scripting language for Java, considered to be used by like 60% of the people who want to use a scripting language within Java. Then we have recently, actually the one guy that came up with the idea of Jython, compiling Python source code to the Java virtual machine, is Jim Hugunin. And he was bought by Microsoft a year ago about. And so he joined the Microsoft Research Lab and is now heading the Iron Python effort, which is basically verifying the .NET 2.0 architecture and the facilities regarding dynamic languages. So there he's doing something similar. He's compiling Python programs to the Common Language Runtime, which is the CLR abbreviation there. And then there's pypy, which evolved in the last 2-3 years. And that's a self-contained and self-translating Python version that is implemented in Python itself. We're going to get into more details there. So these are the 4 main implementations at the moment. And it's interesting to note, that's a common feature in the Python community, I would say, that these 4 projects, even though Microsoft is involved, and even though you have a grassroots effort Python implementation, they are cooperating. They're really like, this year we sat together and thought about what can we share, how can we work together. So on the developer level, at least, there is collaboration. On commercial levels or other levels, it might be different. So then, what is it regarding pypy? Well, first, some facts about it. Started in 2002. The aims were formulated by, basically, at that time, by Christian, Armin, and me, where we invited people for a first sprint in Germany. And a sprint is a 1-week meeting. And we sat together and basically had various aims at what we wanted to do, what we wanted a project like this to be like. And what we wanted to have is a Python implementation that is for research purposes, but also for performance reasons. It's like a project that reinvents a bit the whole language implementation. And the aims are flexibility and being able to try new concepts at the language implementation level, and speed at some point. We were doing that from the beginning with test-driven development, and we, in 2003, basically, we arranged for EU funding because we had grown we had like met several times and decided that if we actually want to do such a project, completely re-implementing the language and then translating it to like down to the processor level, that we really need to work somewhat more full-time on it than meeting every 2 months for 1 week. That just wasn't enough. So we went for that, and there's a whole talk about this tomorrow, how that actually worked out and the community aspects. And currently, just to have a few numbers there, we have like 350 subscribers to the development list. We have around 150,000 lines of code that we wrote. And you're going to see what it all contains. It's quite a lot. And we have around, I think, 20,000 visitors per month on the website. The whole thing is MIT licensed. That means that everybody, each of the participating parties is free to also commercially use it and redistribute it in any way. Okay, so the method, like I mentioned, is test-driven, sprints. It's very much driven by the open source culture. A lot of the developers come from there, have done other projects that have influences on the project we are doing, and that's going to be talked about tomorrow. So the main thing to understand about the implementation is that we do implement the whole language interpreter within Python itself. And obviously, if we just were standing there and wouldn't do anything else, then we have a problem because we cannot really get out of ourselves. We would basically depend on ourselves, which doesn't really work. And so we basically started by using CPython and implemented pypy on top of that and have like a completely correct language implementation. But then we need to do something more. And what we do there is we translate it into lower level languages. In order to be able to do that, it's a dynamic language. It's strongly typed, but there's no type declarations whatsoever. So what we have to do, and that's a major second part of the talk, is we have to infer all the types in the program in order to be able to then translate it to machine-level code, basically. That also means that part of or major parts of our implementation are implemented in some kind of static subset of Python. That what we call restricted Python. It has a lot of, you can basically do lots of things, but what you cannot do is you cannot violate certain staticness conditions. It's not a formally defined approach. It's more like a balance between being able to type infer and not using too dynamic things. But what is very important, and that's a distinguishing feature compared to other similar approaches, is that when you actually start up the interpreter, the pypy interpreter, you can use any Python feature, completely dynamic. You are not restricted at all. And then you have to reach a certain point where your whole program that is in memory is in some kind of static state. All the functions, everything, they have these staticness conditions. So only at that point do you need to be in RPython. So you will find lots of source code in pypy that is completely dynamic. It's using, well, some of you know it, it's using exec statements, dynamically constructs functions, all kinds of stuff. It doesn't matter, because we are not translating source code. We are really working from the program in memory and take this snapshot and translate from there. The architecture, that is the something that we basically came up with in 2002, and the basic architecture is really quite unmodified, and that's not really a surprise because some of the people taking part were very experienced in the CPython implementation and having done extensions and even a just-in-time compiler. That's the one guy that is not here at the moment, I'm in Rigo, did a just-in-time compiler for CPython, implemented in C, very hard stuff. So from the beginning, we had an architecture that was proven to really work quite nicely, and that is, we have the parser and compiler producing the bytecode. We have the bytecode interpreter, basically very similar to how CPython does it. It's completely compatible. Then we have something what we call the object space. You can consider it something like an object library and implements all the operations you can possibly do on integers, on strings, and all this, all the basic types that you need. And the virtual machine basically is comprised of this bytecode interpreter and the standard object space. And then, of course, we also need, because Python is a practical language, there's lots of modules, and in order to be useful, we actually have to have a certain number of built-in modules so that you can do some I/O and printing. Okay, so to visualize this a bit, we have a user Python program, just an arbitrary Python program, that gets into the parser and compiler, that is also completely implemented in Python. Then we produce bytecode, and that is then interpreted by the bytecode interpreter. And actually, can you scale down one? Apple. Oh, okay. Oh, no, it does. Okay, a bit more? No. Okay, what you would see here is that's the scaling thing of the beamer, I guess. What you would see here is that the bytecode interpreter dispatches operations on the object space. So it does not really, when it looks at the bytecodes, it shuffles objects around, but actually to implement integer addition and all this, it just calls this object library, object space thing, and this does it. And that is a very useful abstraction to have that is not present in the other Python implementations. And that is also something that the Perl 6 people are looking into now, and we get to that. So next one. Okay, now you have to scale up a bit. So a few words about the parser and compiler. It takes Python source code, turns it into an abstract syntax tree, which is some kind of structure that represents in an abstract way the whole syntax of the language. Then it takes this abstract syntax tree and generates code objects or bytecode. It works, our parser implementation works from the normal CPython grammar definition, a bit tweaked, I think, but basically the same. And I think at the recent meeting, beginning of December, we managed to actually make it modifiable at runtime. So you can actually change the syntax at runtime. At the moment, you can only remove syntax, but it's also possible to add syntax. Like the print statement always sucked, so we just got rid of that. And I think what is interesting maybe is seeing an interactive command line example, how what it actually means if you have something like code objects in Python. And let's just look at one function. This is a function we're going to use throughout the presentation. It means that you build the sum. It's very simple. You build the sum over a sequence. You start off with a 0 total counter. You go with an index. It's a bit C-like here. You go with an index over the range of until the length of the sequence. So the length of the sequence is something like whatever you pass in as a sequence. And the range builds a list. And this I basically traverses then 0, 1, 2, 3, 4 until the length of the list. And then you sum up, you say the total, which at 0 is added with each sequence number. So you basically build the sum of each of the elements in the list. And you return the total. So if you now, you can import the dis module and see what the bytecode actually of this function is. That's an interactive command prompt. And well, you see the bytecodes, which are evolving a bit from Python version to Python version, but it's also, there are a few optimizations in there. That's why it's a bit harder to read than it actually needed to be. But you see that if you just look at the top, you see it's a stack-based machine. So if you say load const, it basically puts it on the stack. It loads the constant 0. It stores it into the local variable fast. That's the second entry. And then you start some kind of loop. You look at the range function. You get the range function, you get the length function, you apply the length function in the first call function. You apply the length function to the sequence. Then, because it's also on the stack, you apply the range function. And then you get into the for iter, this for e in something loop. And this then basically loops from all the time. And you see here, here you get an item from the list. And here you do an add, which basically works on and you store it again in the total, right? So you get the total, get the eth element here, store it into the total again, and then you go back to the loop. And that is the bytecode, and the virtual machine looks at this, interprets this, and at some point you just load when you're finished, basically you just load the total and return it. So that's the bytecode, how this function is represented. Also, that's interesting because you have introspection. That's command line completion, so you can see actually on the command line, okay, what kind of attributes does such a function have, right? This is a first-class object, so you can see, oh, there's a code object, there's, well, some other stuff, documentation also, and if you go to the func code, then you basically see a bit the low-level details of what the virtual machine sees. You see, okay, it receives one argument, and it has some references to where it appeared in the source code and all kinds of stuff. And then you also see the CO code actually is the binary, yes. This is basically the bytecode that the virtual machine then sees. Okay, so that is the basic architecture. Then the bytecode interpreter sees this bytecode and creates frame objects which contain local variables, global variables, and the bytecode interpreter also implements this control flow. So if you have a for loop and you go back and forth, that's solely done by there's no operation really involved. That's solely done by the bytecode interpreter. And if you have exceptions and things, that's all handled by the bytecode interpreter component of pypy. And if you do something like addition of two numbers or getting an item out of a list, then you dispatch this operation because you're working on objects the bytecode interpreter doesn't really want to know about. You dispatch this to the object library or object space. Yes? Okay, so the object space basically has all the knowledge about the objects that are existing in your program. And it also knows how to perform operations on them. And this is a concept that is then reused for various purposes. First of all, it's used for implementing the language itself on concrete values. And it is not about something like control flow and all the stuff that the bytecode interpreter does. So really, if you want to have different semantics on your objects or optimizations, choosing different list implementations depending on the size of the list or so, that's solely something that the object space can do, and the bytecode interpreter does not need to know anything about this. And for example, it also provides a means, there's an example on the website doing that in 100 lines. You can basically modify the existing object space so that you have lazy evaluation in Python, which, okay. Okay, then, like I mentioned, for practical reasons, that's not really an architecture thing per se, but for practical reasons, we do need to have a lot of built-in modules to actually have our Python interpreter run, which is I/O and some file operations and all this. And that is done, that works, although there's still quite some things missing, especially socket and network communication, and that's being worked on at the moment. But well, there's a lot of modules. The Python library has like hundreds and hundreds of modules, and also implemented in C. So we are basically porting from C to Python, which usually means like ripping out lots of stuff. Okay, so just to make this point very clear, because it's going to be the basic thing about the, how the second major part of the pypy project actually works. So we are still talking about the language implementation here. And we have the same function I just showed. And you see this guy there on the left is the interpreter. So it sees this source code, and we have a sequence that was passed in here. This is this one. And it walks over the list. And this is basically the frame state in the virtual machine that records all the local variables. So, and at some point, it returns. The interesting thing is here, this was a concrete example. And if you go further, then seen from the I'll just continue. If you now look at the same thing, then you see what happens with the object space. Because here, just do the next step. You see that these operations, these numbers now are passed to the getItem operation of the object space by the bytecode interpreter. And then the bytecode interpreter assigns, okay, I know that item is now 6. In the next step, it takes the 0 and the 6 and adds them. This is this line in the source code over there. And this is the current value of total, right? So this shows that the interpreter looks at this and sends the operation to the object space and keeps the name to value bindings, but doesn't really need to care. The reason this is interesting is because the bytecode interpreter really doesn't know anything about numbers or something like this. The only thing that it can ever get out of an object space is knowing if some object has a true value or a false value. That's the only information the bytecode interpreter can ever get, and that's only needed for implementing branches. If you have an if statement or while loop or something like this, then the interpreter who implements this control flow needs to know, what is this object? Is this now true or false? So it can basically branch in two directions. And the next step then is that we have something like the fruit object space, which means that the bytecode interpreter sends some fruits to these operations and something happens here. So if these are sent to the getItem, the getItem operation, the bytecode interpreter really doesn't care. It just passes them to the object space, it does something, it's black box objects, and it goes back.
Of course, it doesn't really exist, this fruit object space.
Yeah, we haven't actually implemented this fruit object space. That's a bit not so easy. Okay, so that is basically the language implementation, the basic architecture of how pypy works. And I pass on to Carl now, who talks about the second major part.
Okay, now we have this cool Python interpreter that Holger described the architecture. And now we have the problem, it's written in Python, and it runs on any other Python interpreter, but of course we need a way to get rid of this circularity. And as Holger already said, the technique to do that is to take this implementation of a Python interpreter, which is written in a special way. It's a bit more static than usually the Python code is usually, and take this and transform it in several steps, and in the end arrive at low-level code like C code, or we have implemented several backends, so we can transform the interpreter into several languages. But yeah, I mean the C backend is the most important one, and there are basically several steps. The first is we produce flow graphs out of our program. We do that with a special object space. I'm going to talk about that in a second. And then we use type inference to find out the types of all the variables that are present in the program, because the problem is, of course, Python is dynamically typed, so we do not know per se what the types of variables are. And basically then the problem is the Python type system does not necessarily match the type system of the backend. So we need a special transformation that replaces operations in the Python type system with operations in the type system of the backend. And in case of C, that's the LL type system. And then we also have the OO type system that is used if you target like higher level languages. I'm coming to that too. And now, next slide. Here is again the overflow. We start in the upper left with handwritten RPython code that is then transformed into a flow graph. We perform type inference, which is then specialized in, and have an annotated flow graph, which is then specialized into a low-level flow graph that contains only operations of the that fit the backend, and then we generate code of that. So that's just an overview. And now I'm coming to the first step in this process, which is abstract interpretation. And the idea is that we reuse our bytecode interpreter with a special object space to interpret our own interpreter, like the whole. And as a side effect of this, of this interpreting with the flow object space, we get flow graphs, like regular flow graphs in a regular computer science sense. And the idea how to do that is that the flow object space implements abstract operations. So it has abstract objects, which are variables, and they get added, for example, and the result is a new variable. But at the same time, an operation is recorded, and that is then put in the flow graph. And one of the really peculiar things of pypy is that we do not start from the source code. Holger mentioned it already. We don't look at the source code of our Python interpreter and start parsing it and whatnot. But we start interpreting the whole program. And at one point we say, okay, stop. Now we analyze all the live bytecode objects that are right now in memory. And until that point, we can do all sorts of magic. And it has a lot of nice consequences. And one of them, for example, is that if you have syntactic sugar that's just in a parser and that gets then transformed into the same bytecode, we don't need to change our parser anyway because it's just done by the regular bytecode compiler. And now to make this this object space a bit clearer, we have again the same picture. And now we have the special flow object space. And here, all the values that are in local variables are again abstract objects, and they're just called A, B, and C. Okay? And if now you perform a get item on B with C, you get a new variable D. And if you add some variables, then you get again a new variable. Go on. And as a side effect of this interpreting, you get these operations recorded. So when the interpreter, together with the flow object space, interprets this program, I mean, there will be more operations than just these, then in the end, you get a flow graph that contains operations on variables. Okay. Then, now we have flow graphs, and the next step is to perform type inference on these flow graphs. And the algorithm we use is a forward propagating type inference. That means we start with known types. For example, all constants have known types. You know that the type of 1 is an int, so you can start there. And you also know the type of the entry point function. You say, okay, please start the type inference at this function, and look at all the functions that are called. And this function, the types of these of the arguments of these functions are int and whatnot, bool or list or whatever. And it then goes on from this point and reasons about the operations that are performed. For example, if you have addition of two things that are known to be an int, then the result will be an int2. And if you have a get item onto a list that contains ints, then the result will again be an int. And the type inference engine assumes that the types that you use are static, so a variable doesn't change type. And the idea is that you start from very special values. For example, if you see a is equal to 1, then you assume that, then you know that a is an integer and its constant is 1. And if at a later point you say a is equal to 2, then you get more general. You say, okay, we still know it's an int, but we don't know that it's a constant anymore. And you generalize and generalize until nothing changes anymore, and then you have reached a fixed point, and then you know the types in your program. Now we are at the step we have flow graph, and we know for every variable what type it has, and now we have to make sure that the backend can do something with these types because they are still Python types. They are lists and dictionaries and whatnot. And the backend cannot. I mean, in C, there's no such thing as a list and as a dictionary. So you have to transform these types into to fit the type of the backend. And right now we have two type systems. There's the LL type system and the OO type system. The LL type system is a type system that fits to like C, very low-level languages like C, and currently we also target LLVM, which is a low-level virtual machine. It's a very interesting project too. And the LL type system contains types such as you have structures and arrays and pointers and function pointers and the usual stuff that you find in C. And then we have the OO type system to target object-oriented languages like Java and JavaScript, Smalltalk. And the idea there is that you have classes and instances and you can call methods and all that usual stuff. And after this specialization step, you have specialized flow graphs that contain only operations that fit the backend, like fit C, for example. And now we come to the backends. The backends start at where the specialization left off. We have a specialized flow graph, and the backend basically takes these and produces code in the target language. Currently, we have two complete backends, which is C and LLVM. And we are currently working on two more backends. One of them is JavaScript backend, which also kind of works for medium-sized examples already. And we have a Squeak backend that we're currently working on. And in these backends, you also have to support foreign function calls, like stuff that really can only be implemented in the operating system. And for that, you need small, very small, manually written code snippets. And yeah, I think all in all, we have a couple of hundred lines of C code in the whole project. So, and now we are going to.
You set this up, and I ask if somebody has questions. Yep. So until here, now we're going to show larger examples of all these flow graphs and code generation. Are there some fundamental questions already that you want to ask?
You mentioned porting some of the built-ins from C to Python. I was wondering if you talked about your experience in doing that. Did they get shorter? Did they get simpler? Did you find bugs?
Oh yes. So that was we did actually find a lot of bugs, and especially in the parser and compiler, which we took from CPython, the compiler package. It basically delayed some of our project for 1 or 2 months because we had to fix a lot of bugs basically in there. And also when porting things from C to Python, it gets a lot simpler. So all the built-in functions and all the, also part of the I/O handling and all this is a lot easier to read basically. And there were a couple of bugs fixed and also backported to CPython even. So basically there's some stuff already that is back into CPython that came from pypy.
I think it's also, in generally, we tend to find lots of bugs in CPython. I mean, we have found within the project something like 4 or 5 seg faults in CPython, which is something that regularly should never happen. But you try to find out some obscure detail and crash CPython's down. And okay, another one or? Yes? Do you want to try it? Or tell me, I'm going to tell. How do we find a fixed point? That's a tricky question because it's really. Sorry? Well, this is really a difficult question. The question was, how do we know whether we have found the fixed point, whether the variable does not get more general anymore? And basically, the general idea is we know that the change of one variable affects another variable. So we reach a fixed point if something changes, we generalize the variables that depend on that change again. And just at one point, there will be no changes left that need to be propagated. And I mean, it's really getting a bit too detailed into the how annotation works. But if you want to, we can discuss this. Yeah, of course. I mean, the point is we go only from special to general. We never go in the opposite direction. So it's certain that we will reach a fixed point. Okay, to this example, it's the function that we have already seen. we loop over the length of the list and sum the elements. And here, the list, which you can see here. One moment. Yes. On the bottom, you can see the types that were inferred for the function. Here, for this sequence, the annotator knows that.
You want to have full equipment now?
Oh, cool. For this sequence, the annotator knows that it's a list, and it's a list that contains only integers. And, well, it doesn't help because I need this. And then we call the len of this sequence, and the result, the length of a sequence is an integer. And then we call a range, which is again a list which contains only integers, and then we iterate over that. And maybe I can zoom out. Yes, here you see basically the full flow graph of the function. You see here is the loop. You loop here until you're finished, and then you go out there. This is the return block where the return value is put back to the, oops. Okay, basically here you construct the iterator, which is, well, some iterator, and here you call next on it, which returns an int. Yep. And here you perform the get item. You get the v5 item, out of the sequence, which is stored in the variable v6. And then we add v7 and v6 to v8, which is then flown into this block back again. Then you go back here for a while until at one point where the iteration stops, the stop iteration exception is erased, and you end up here. And you can see that, one point you can see is that here you add an int and an int, and the result is again an integer, of course. And in the end, you can also see that the return type of the value is also an integer. So this was after flow graph construction and annotation, type inference. Now we're going to look at the flow graph after specialization. Good. 1 second. It's now generating flow graphs, performing type inference and specialization, and it's now creating code and now compiling, and it's finished. So it's a rather small example, so it's rather fast. We have again the sum function here. Oops. Okay, this takes a while for obscure reasons.
Yes.
Yes, good.
Well, the thing is maybe
It takes a second. The problem is we need network access for obscure reasons.
explain the obscure reason.
Yeah, you can.
Okay, the obscure reason in 20 seconds. The obscure reason is that the graph-vs library is broken since, I don't know, half a year, because we generate these huge flow graphs. There's some syntax in there that breaks it. And we also submitted a patch, I think half a year ago, but it didn't get accepted. So we have a server in the network that if graph-vs crashes, we contact via HTTP this server, have the patched version there, send the stuff back. Because we don't want to require everyone who uses this. You just can install standard components. We don't want to require everyone to install a patched version of a library, right? Okay, so we have a very practical approaches to certain problems.
Of course, it can take an arbitrarily long time, especially if the connection is bad. And therefore, we will maybe look at the generated C source first. And let me just warn you, the generated C source is very scary. There. Yes, good. So first at this. Basically, you now have, yes, that's a specialized flow graph, so it's specialized for C. You now have stuff like signed, which is not just an integer, it's a signed integer. And you have a pointer to a GC struct range, which contains a start, which is signed, and stop, which is signed. And you call function pointers here. This is a function pointer to something. And you pass in stuff, and then you have the same structure of the flow graph, but the operations, down there, you cannot see it because it's too small, but down here you have something like int add. Here you have incorporated the information that these two variables are ints, so you add an int, and the return is again assigned, and that gets returned. And I also want to look at the source code. As I said, it's kind of scary. We produce pages and pages of stuff. Yeah, of course, you would write it like that too. And here you have, in the end, the function. It basically, the blocks, I mean, it's not mapped to any control construct anymore. You just have blocks, and you have gotos between the blocks. And here you call new range and range iter, which you see, no, not here, but nowhere. For the function itself? No, never mind. Basically, here you have the first block, and then here you have the loop. Basically, where is it? The add is somewhere too. It's really a bit hard to navigate. But it's usually never looked at, so we don't care. Yep, here's the add. And above it is the get item. Here you get the item out of the list, and then you start adding, and at the end you return here. Okay? No, where were we? Here. So now we come to a very important and very, oh, I have to speed up, right? Okay, we have a very important concept within pypy, and this is one of the concepts that makes pypy quite different from other language implementations. And the idea is that we want to make implementation decisions for the implementation of the interpreter very late. For example, what GC are we going to use? What threading models are we going to use? What calling convention are we going to use? The idea is to make it not at all, make these decisions not at all during the interpreter implementation. This is not true, for example, in CPython, their reference counting is used. That means at every point in every file of CPython, you see that you use reference counting, because all the time you have in-graph, degraph, in-graph, degraph. You need to be very careful to not make mistakes there. We don't make this decision at all. Nowhere in our interpreter you will find an idea what GC we are going to use. So the idea is that these decisions are then later at translation time weaved into the implementation. So we take this RPython implementation of a Python interpreter, translate it to C, and weave certain aspects in. And one aspect is we can choose what GC we are going to use. And it's very important, this is completely independent of what language we're implementing. And currently we're implementing a Python interpreter, but if we implement in RPython, whatever Lua interpreter, we could weave in the same manner different GCs, different threading models, and so on. Thanks. For one of the aspects we're really targeting is memory models. Currently we have implemented two different garbage collectors. One of them is ref counting because it's very easy. The other one is just to use the boom collector, which is also very easy, which is a very tuned garbage collector, conservative garbage collector for C. And we're currently working on more general and exact GCs, which will also be written in Python. And there's a framework for it there, but it's not yet integrated into the rest, so you cannot use it in pypy, but it's on its way. And we have implemented a copying garbage collector and a mark and sweep garbage collector, and possibilities to do much more and sophisticated algorithms. Okay. Then another important translation aspect is threading model. Currently we have the very important choice to have no threading, because threading sucks. And you have the choice to have a global interpreter lock, which is the same technique that CPython uses. Basically, you have a lock so that at one point only one Python program can be interpreted, which is not optimal, but anyway. And in the future, we plan to implement as a translation aspect more free threading models with more fine-grained locking. And another aspect that's related to threading models is stacklessness. Christian Tismer wrote the stackless. Raise your hand. No, Christian Tismer wrote the stackless patch to CPython, which is basically a patch to not map Python user level recursion to the C stack. So you can have in an interpreted program arbitrarily deep recursion until your heap runs out, and this is not reflected in that your C stack is growing and growing. And we can also translate our interpreter into a stackless style, into continuation passing style. That means at any one point we can say, okay, our C stack is growing too big. Let's store it all away. Let's put it all onto the heap. Then the stack is empty again, or nearly empty, and then we can make recursions that are arbitrarily deep until our heap space runs out. And it's again important to note that this is only implemented as part of the backend, so it's very little code. It was written in a second. It was written in like 3 days or something, just as a tweak to the backend, and now can be used for the interpreter. Yes? Does it break your debuggers when you do things like that? Sorry? Does it break your debugger? Break? I mean, can you see the list of the functions? Yes. Yes. The question was, can we still use a debugger? Because, I mean, yes-ish, no. Basically, the point is we never used the C level debugger because you...
Yes, sure.
Yes.
Yeah. Just the question is about debugging aid for all this, generated things. And the case is that we have lots of debugging tools at various levels. But also we have, for each of these things we are doing, we have small examples. So when Carl said, for example, this is all scary code, C code, we don't really look at, it's actually true. Because we have only small examples that we are using for unit testing. And then we have if you find a problem, we actually write a unit test and check that the translation works for this correctly, including GC and all this. And after this little piece runs, we go to the next thing. So actually, at one point, we jumped from 1% to 100%. We had lots of little snippets, and then in the end, the whole 1.3 million lines of code was just working, except for one bug, which was some weird, I think, compiler issue or so. But anyway, let's just continue to...
okay, and this slide, basically the idea of... was this the pointer? Yes. The idea of having this translation aspect is compared to other approaches like JVM and Java. First, I'm going to tell you what these rows are. Basically, here is the project. Here is the number of languages that is implemented on this platform, project, whatever. This row is the number of environments that the project targets. And this is the number of implementation aspects that you can choose. And first, we're going to look at pypy. Pypy currently implements one language, which is Python, but it would be conceivable that you could write a Lua or Ruby or whatnot interpreter in RPython, then you would get all the other pypy benefits too. And the environment it runs in is variable because we can implement various backends. We can implement a Java backend, then it runs within the Java environment. We have implemented a C backend, it runs in this regular Unix C environment, Windows 2. And we can implement a .NET backend and a Smalltalk backend, whatnot. We have these implementation aspects like GC and threading that we talked about. And then we have, in contrast to that, the idea of the JVM and .NET is to force the environment to one. Basically, JVM and .NET say, okay, please everybody use the JVM. So we have some languages there. I mean, there are some languages that are implemented on JVM, but please all use the same infrastructure and whatnot. And yes, and the same is basically exactly the same approach is what .NET does. Say, okay, everybody runs on the CLR, and yes, and we believe that this is the one important difference that between pypy and other VM approaches. Yes, okay, I think it's Holger's turn again.
Yes. Okay, so just a few, or maybe a last comment about this. One developer who's also involved with Python and Java stuff said that. With .NET stuff, said that yes, it's many languages as long as they behave like C#. Okay, so a bit about back to the overview of the project. We had 3 public releases in the last, 14 months or so, 12 months. First one was a quite compliant Python implementation. Then 0.7 was a few months later out, was a compliant implementation of pypy. and also completely self-translating to C. That's why I mentioned the 1.3 million lines of code that were generated and just worked. Then we have, with 0.8, we have the full parser and compiler. That's the delay. We actually wanted to have that in 0.7. And that's also 0.8 because like the community is always complaining about the speed issue. There was quite some work on like 1 or 2 weeks on optimizations because we were really more about correctness and getting everything to work at that point. And then it was the 0.8 release was like 10 to 50 times faster and felt probably something like 500 times faster because before we didn't really have a full parser and compiler and had to pull some tricks there. So in 0.8 that's actually quite clean then. Then there's a lot of documentation by now, also EU reports that we just finalized before Christmas, and they're actually quite, I mean, there's some scientific reports and some implementation reports also summing up a lot of the documentation we have, and we're probably going to release that as well. So that's not only used by the European Union. And there's also by now a number of talks and slides and architecture documents and things where you can read, and there's an IRC channel, so you can just join in and ask questions there if you are stuck in some paper, want to understand something or so. Then maybe also a bit more about with which projects we're having some influences with. There's the Perl 6 thing, I think it was a mail from October, where somebody, to our joy, basically said that they are now looking into the object space abstraction and how we're doing that. So it's the very basic thing I explained earlier. And we also have LLVM, which is also listing pypy now as a major project, actually as a major example for their low-level virtual machine. And the guy, Chris Lutner, and they're helping us a lot, actually. They're very responsive, so we find bugs and they fix it within a day. And he's now at Apple, and they actually, I think, want to integrate LLVM into GCC now. That's a recent development, that they want to implement the optimizations of LLVM into GCC and are talking to the GCC developers to actually get this integrated. So there's a lot of stuff going on in that area. And then there's IronPython I mentioned just earlier. Let's just go to the next slide. One thing, the speed issue, that's kind of interesting. It's a constant issue. It's brought up all the time. It's a frequently asked question. And we haven't really started with serious optimizations, and we are only now starting to generate a just-in-time compiler, which is going to help for application-level programs. It is actually true that you can, like, if you translate the RPython programs, which is our whole language implementation is majorly implemented there, if you translate that, then you get 10 to 100 times faster compared to running on top of CPython. So it is actually, you can translate this to C and run it very fast. And actually, Christian went to a US company 2 months ago and ported. They wanted to had problems in very performance-critical code, had Java code. So in the end, Christian decided to just port this to RPython, right? Translate that, tweak it a bit, and it was actually then running faster than it ran on Java. I don't know the factor actually, but it was so impressive that they are now thinking about ways how to fund us, which is not so easy because of the European Union and whatnot. It's quite complicated, but anyway, there's really some interesting possibilities, and we are thinking about releasing this translation tool by itself, but it's also a lot of effort to actually make it usable for more general cases, so that's not really completely clear if we're doing that. Then, regarding the project framing, what we are aiming at for 2006 is definitely the just-in-time compiler. That's the toughest effort at the moment, and that's the one where you saw the picture of Armin Rigo. He wrote something like this for CPython, and we are seriously doing stuff there now. Then more stackless, non-C calling convention things, which is especially interesting for gaming engines, having millions of micro-threads where objects can communicate and all this. Also work where Christian has worked. And then things like experiments, we have done something in that area, which is now too short a time to show the example. Orthogonal persistence and distribution. So for example, with there's a special object space, 100 lines code of implementation, and you have objects distributed, and you can work completely locally, no CORBA, no RMI, no remote method invocation, nothing. You can completely work locally, and the language acquires the objects from the network for you, and they basically cluster. So you can have a list of objects, and once you iterate over them, they are all acquired, and then they're in your machine. And if somebody else has a reference to the same list, he will reacquire it sometime later, and it's completely transparent. So at the Python level, you just see your program, and it has all these objects, and you can even say, what is the type of this object, and it's a list. It's nothing special. It's completely transparent, and that's what we call orthogonal. And that's also another effort is going into the direction of building security at the language level into it, so that it's you don't have to subclass anything or so. It's really done at the language level and below. So you just have security roles and all this very cleanly implemented, and maybe as a translation aspect, in your binary that you have specialized for high security applications. And then, like the whole project, you're going to hear more about the whole project if you want to tomorrow at, I think, 2 p.m. The first thing we have to do is we have to survive the EU review on the 20th January in Brussels. There has been a lot of work on that. And then we also want to think about better interactions with the community, and we want to think about what actually do we do after the funding ends, because the project is more than just the EU funding. There are lots more people involved also worldwide. And we do think about ways to actually, how do we continue and how do we distribute some money to contributors and all this, and that's a bit involved, and we are trying to improve there. And also we have, it's also more for tomorrow, we have visits planned now to the US in February and Tokyo in April or something, and yes, I know, just want to, and then there's commercial opportunities, but yes.
I have a couple of questions. First question, you mentioned lists of integers. Are those magic built-in types, or do you have something like algebraic data types for your analysis? It's, there was some optimization. I distinctly remember seeing in the graph.
You mean R-Python integers?
Yeah, in the R-Python flow graph, in the type analysis
Yes,
in the flow graph.
they turn into regular C integers.
What? It's, yeah, I know that they turn into regular C lists at the end. The question is, what's the nature of the type you're operating on? What's the type system? Is it a list of integers? You must figure out you have a Python list and you have integers in it some way by inferring the type. The question is just, is there some magic list of integers in your type system, or is the type system smart enough so it will figure out it's a list of integers, or it's a list of foo objects, or it's some weird structure where the second element happens to be an integer? Does it do that?
Yes.
Okay. The next question, I assume that R-Python doesn't include things like eval or creating new objects at runtime or any other dynamic stuff. How much of a pain in the ass is it to write R-Python compared to regular Python?
Basically, it's true, you cannot dynamically execute code easily in R-Python. You can actually do some things. We are using normal Python code from R-Python, and it's doable, right? The pain is, I would say the main pain is, the main pain is good. The main pain is exceptions. We didn't go into those details, but we do use native exceptions in R-Python. But we have to distinguish between exceptions that are really at the, in your user program, if you access something in a list and it gets you a key error, right? That's a user level exception. And we also have something like a key error in our R-Python implementation. So we make a sharp distinction there, and we say that everything that comes from this application level user program is wrapped into an operation error instance. So what you see in the bytecode interpreter is do some operation, like try, do some operation, accept operation error, and then you have to see, okay, does this operation error contain a key error, right? So that's a bit painful, because you cannot directly say, okay, do this, unless I receive directly a key error. You see what I mean? So that's one pain, and the other pain is, there's a few issues here and there, but for example, you have complete control flow, you can use lists, dictionaries, lots of stuff. You just have to make sure that, for example, you don't say L equals 3, and then L equals some string. That violates basically a staticness condition, right? And that's usually that's clean code anyway. You shouldn't like mix types like this. The question is, does the compiler notice that problem? Yes, it does. The better question is, how good are the error messages? We worked on that, so it's actually not so bad anymore. It's really a major, that's some of the problems we have with LLVM, for example. It's a very good thing, but the error messages, if something gets wrong, is more or less like something failed. You know, and that's, no, so yes, it does notice, it crashes in some way, and we try to make them usable. But again, we are not aiming, or our initial aim was not to have this translation tool become very convenient, just good enough to translate ourselves. That was the initial goal, so. Somebody else? Time is over. Okay. Then, thanks a lot.